In this video, we're going to talk about finding greatest common divisors and least common multiples using prime factorizations. So let's say we want to find the GCD of m and n, and we have m and n either factored already or we need to factor it into a product of primes. So let's say that the m is factored into the primes p1 out to pr with the appropriate exponents I1, I2 out to IR on each of them. Same thing for the n, but just using different letters for the prime. So we'll use q1, q2 out to q sub s with the exponents j1, j2 out to j sub s. So we know that, if m and n are going to be different numbers here, otherwise finding the GCD would be really easy. So we would expect that the list of primes here should probably be different. We wouldn't expect as many distinct primes in the factorization of m as we have in the factorization of n. So we would expect these factorizations to be different in lots of possible ways. However, I can still create a list of primes that I can use in common to write a factorization for m and a factorization for n. Not necessarily unique factorizations, if you will, because I'm going to be putting in ones in different places. But I can still use the same list of primes in my factorization. So what do I mean by that? Well, let's say we have the numbers 60 and 70. Well, the 60, if I write it as a prime factorization, is 2 squared times 3 times 5. And 70 as a factorization is going to be 2 times 5 times 7. So my list of primes that I could use here would be the primes 2, 3, 5, and 7. And then I can insert a 7 to the 0 in the factorization of m, and a 3 to the 0 in the factorization of n, because those are the primes in the one that's missing in the other. So then I have the exact same list of primes that I'm using in the factorizations for m and for n, and I haven't changed the numbers at all because all I've done is multiply by 1. So, like I mentioned just in that previous example, we can change our factorizations if necessary to where our list of primes here are the same list of primes for both numbers, and I have the same, so since I have the same list of primes for both numbers, I have the same length of number of distinct primes in the factorizations, so I can use the same subscript here, t, in both places. I can then have the appropriate exponents for both the p's for the m and both the p's for the n, where it is entirely possible that we have some of those exponents as being zeros. Okay, so going back again to the previous slide, the example of one of them being 0 here for my m would be that 7 to the 0, because I've inserted that prime in there that wasn't there before, so I need to make sure that I'm keeping everything equal. So really I'm only multiplying by 1. Likewise for the n when we inserted the 3 in the factorization. All right, so how can we find the greatest common divisor then using this new factorization idea? Well, now I can just compare my primes as I go from left to right and pick out the biggest power that's possible that divides both of them. So let's look at the specific example, and then I'll go back to the formula that I have written here. Going back to the example that we had before, we had 60 was 2 squared times 3 times 5 times 7 to the 0. My 70 was 2 times 3 to the 0 times 5 times 7. Let's start with the first prime here of 2. That first prime here of 2, I have a 2 squared that divides 60, but I only have a 2 that divides 70. So the biggest power of 2 that I can use that divides both numbers is just 2 to the first power. Looking at the second prime, 3 in this case, I have a 3 to the first for 60, but a 3 to the 0 for 70. So I really don't have a 3 that divides both numbers. So I'm going to use the 3 to the 0 because that's the biggest power of 3 that divides both of them. 5 to the first divides both of them, so I would have 5 to the first as the biggest power that divides both. 7 to the 0 for the first one, 7 to the first for the second one. 7 to the 0 is the biggest power of the 0 is the biggest power of 7 that divides both of them. So going back to what my general formula looks like here, I look at the first prime, I take the smaller of the two exponents and put that on my prime to give me the power on P1 that will divide both numbers. So that's the biggest that divides both. Okay. Likewise, if I go to the second prime, I'll pick the smaller of the two exponents, put that on the P2, and continue across until I get to the last one, and that will be my GCD for both numbers. So again, going back to the example, we had 2 times 3 to the 0 times 5 times 7 to the 0. We get 10 as our GCD, which is a pretty quick check to see that we really do get that for the GCD in this case. Let's look at a second example where we have two numbers already given to us in prime factorization form and asks us to find the GCD. So we've got 2 to the 6th times 3 squared times 5 times 7 to the 5th times 13 for the first number. We've got 2 to the 4th times 3 to the 7th times 5 cubed times 7 to the 5th times 11 to the 4th for the second number. So again, I can think about using both both sets of primes to get a list. I don't have an 11 here that I do over here, so I can think about an 11 to the 0 in the first one. Likewise, I can think about a 13 to the 0 in the second one. So again, just go across with your primes and pick out the smaller of the exponents. That will represent the biggest power of the prime that divides both numbers. The smaller exponent will do the job. So first prime here is 2. The smaller of the 2 is the 4, so we'll use a 2 to the 4th in our GCD. The second prime is 3. The smaller of the two exponents is 2, so we'll use that in our GCD. Looking at the 5s, the power is 1, that's the smaller one, so we'll use a 5 to the 1st. 7 to the 5th is in both of them, so I can use a 7 to the 5th in the GCD. I don't have an 11 in the both of them, so I'm not going to use an 11, and I don't have a 13 in both of them, so I'm not going to see a 13 here. Again, you can think of that as 11 to the 0 and 13 to the 0 if you want. But again, both of those will be 1, so there's not any real necessity for writing those two things. So our GCD here will be 2 to the 4th times 3 squared times 5 times 7 to the 5th. And if you put that in your calculator, you get 12,101,040. Let's switch gears and look at the least common multiple of m and n. And let's say, just like we did when we had the setup for the GCD, we have m and n written in factorizations in terms of the exact same list of primes. Again, we wouldn't expect all those exponents to be the same. We'd probably expect some of them to be 0 as well, but have it listed the exact same way that we had in for the GCD. Then when we're looking for the least common multiple, we want the smallest thing that is a multiple of both. Well, if we can approach this in the same way like we did for the GCD, except in this case, we need to make sure that we pick the bigger of the two powers because we want to make sure that we're a multiple of both of the prime powers in both numbers. We can't pick the smaller one because that won't be a multiple of the bigger one then. So to get the smallest thing that works for both, we'll pick the bigger of the exponent for each of the primes as we go across. So we'll have the LCM as the prime P1 to the maximum of the two, P2 to the maximum of the I2 and J2, and so on down the line. So we'll pick the bigger exponent and put that on our powers of P. So let's go back to the first example that we did and see how to find the LCM in that case. Again, we had our prime factorizations of 60 and 70 and added in the primes where we needed to that were missing from one or the other. If we look at the first prime of 2, the bigger of the exponents is 2, so we'll use a 2 squared. The bigger of the exponents for the 1 and the 0 is the 1, so we'll use a 3 to the first power. Likewise, we'll use a 5 to the first and a 7 to the first to get 420 for our LCM. If we go to that second example we did with the longer prime factorizations, again, same idea here. We look at the 2, the bigger exponent that we see on the 2 is the 6. On the 3, the bigger exponent is 7. For the 5, it's 3. For the 7, it's 5 on both. 11 is missing in the first one, but we still need to make sure that we are a multiple of this 11 to the 4th as well. So we use 11 to the 4th in that case for the LCM. And then likewise, we use the 13, because we need that as well to make sure it's a multiple of both. And then if you multiply this looks like a great job for a calculator or a computer. It looks like we've got something near 56 quadrillion. In any event, this is how you find the LCM and the GCD when you've got prime factorizations. Again, for GCD, we'll pick the smaller. For LCM, we'll pick the bigger of the exponents and put those on the primes that appear in the factorizations of the two numbers. Using this idea, we notice that we have the relationship that the product of the two numbers must be equal to the greatest common divisor of the two times the least common multiple of the two. So think about why that's true. If I multiply m and n together, well, you would add your exponents. You would have I1 plus J1 here on your P1. You would have I2 and J2 on your P2, and so on down the line. Well, when you multiply the GCD and the LCM, you're going to get exactly the same thing because one of them has the smaller of the two exponents, the other one has the bigger of the two. So there's going to be the same two exponents. They just may not necessarily be in the same order that they were when you multiplied your m and n together, but they're still the same exact set of exponents that you have that you're going to add together as you did when you multiplied the m and n together originally. So you get the relationship that the product of the two numbers must be the same as the GCD and the product of the GCD and the LCM. So again, as just one last time, we note that if we take the product of 60 and 70, we get 4,200, which certainly is the same thing as 10 times 420.